Good morning, everyone. My name is Dmitry Petrovic, and I'm from the International Nanotechnology Laboratory, INL. So I will be the host for the seminar. It is a second seminar in a series of seminars related, organized by the INFRACHIP project. And this particular series is dedicated to the technology platforms offered through the INFRACHIP project that are related to various types of sensing capabilities. And specifically, the seminar today, as you see from the title, is going to be about the integrated photonic platforms. Or more specific, let's say more generally about the photonic integrated circuits. And in terms of the topics covered, the seminar will include some of the historical perspectives, and it will mention three of the important material systems on which the photonic integrated circuits are based. And of course, there will be several examples of the different sensing applications, of things, whether it's something, let's say, more high TRL, like the LiDAR systems, but also some of the things related to gas sensors, so microfluidics or gyroscopes and so on. And another aspect that will be covered here is going to be the integration, because, of course, again, the variety of different active components that are necessary, plus the electronics and so on, actually for the modern sensing applications require a fair bit of integration, both between the photonic and the non-photonic components. And I'm happy to introduce our speaker, Mateusz Słowikowski, and he's a graduate of the Faculty of Electronics and Information Technology at the Warsaw University of Technology. In 2022, he defended with distinction his PhD thesis entitled Integrated Photonic Interrogators for Applications in Fiber Optic Sensor Systems. And his areas of research interest include photonic integrated circuits, fiber optic sensors, and fabrication technologies for photonic integrated circuits and electronic components. He has authored and co-authored more than 100 publications and conference presentations. And he also spent some time at an internship at the IMEC Research Center in Belgium. And since 2015, he has been associated with CEZAMAT. And CEZAMAT, of course, is one of the partners in the INFRACHIP project. So again, just as a final reminder, so keep in mind that if you find some of the platforms described in today's presentations particularly interesting, it is possible to request access to those platforms through the INFRACHIP project. And of course, we will have a question and answer session where you can ask some questions at the end of the session. But also, if you contact us or the project after the session, we can, let's say, discuss if you have some particular ideas of how you can take advantage of the access to these platforms offered by the INFRACHIP project. And now, without further ado, I will hand over to Mateusz.
Thank you for a kind introduction. Starting from what is CEZAMAT for a few seconds, we are part of Warsaw University of Technology, and we are bringing the gap between the fundamental research which are taking place at faculties and industrial application, because we have quite nice laboratories equipped with CMOS pilot line. And here is the list of our, more or less list of our tool. So as I mentioned, this is fully equipped CMOS line compatible with 2, 4, 6, and 8-inch wafers, starting from batch spray system for automate cleaning surface of wafers, and wet etching, then tools for layer deposition, deposition with PCVD, LPCVD, and magneton sputtering. Next, high temperature furnaces for oxidation, annealing, diffusion, then rapid thermal processing, electron beam lithography tool, which allow us to go below 50 nanometer with dimensions of element. Next, mass aligner for photolithography processes in E-line, reactive ion etching plasma system. Next, classical photomask cleaning, not classical photomask cleaning device. Next, ion implantation and characterization, optical and electron microscopies, ellipsometers, and profilometers. So, what is photonic integrated circuits? They are devices which consist of different optical elements which are historically separate. So making all these elements in one circuits give us advantages as compactness, low power consumption, high reliability due to lack of mechanical elements, mechanical connection, reduction of packaging costs, of course, if we are thinking in thousands of pieces, and low manufacturing and maintenance costs. Also, of course, in proper scale of the production. And as you can see, this photonic integrated circuits are quite small. They are typically few by few millimeters. And in similarity to the electronical integrated circuits, we can build them from some basic building blocks. In electronics, this is transistor, capacitor, resistor, electrical connection. And in photonic building blocks, we have optical amplifiers, polarization converters, phase shifter, waveguides. And based on that elements, we can simulate and fabricate many different photonic integrated circuits for different applications. We can divide photonic integrated circuits in different groups. One type of dividing is dividing them for in case of material platforms, which go to the point that we have passive and that we can have in this platform passive and active elements. So mentioning the most important platform, first is silicon photonic, which is passive platform, indium phosphide and related materials. This is active platform. Next, we have general silicon platform, which is silicon nitride on silicon oxide, German silicon, the family of silicon photonic platforms, which are passive. Then there is a gallium arsenide, titanium oxide, and polymers, which are passive. And they are hybrid heterogeneous platform, which are active. Going into silicon-based platform, we can here see the comparison of the library of elements available for the main material platform, for the main silicon material platform. So you can see that we can have waveguide, couplers, modulators in most of them, not in silicon nitride. Then we have filters like ring resonators, arrayed waveguide gratings, and filters based on Bragg reflectors. And of course, with some heterogeneous integration, we can have active elements, but only photodiodes. In silicon materials, we cannot have active elements like lasers and optical amplifiers. With silicon nitride and generally in silicon, you can see the comparison of dimensions of this element. And what I want to highlight is all that elements are, all that critical dimensions of these elements are below 1 micron. So this go to some kind of problems in technology, because we cannot use classical standard photolithography. We need to go to the more advanced techniques, and also the small dimensions make some additional difficulties in etching. Going into a little bit of history of these optical elements, the idea of integrated photonics, it's not so new, because first attempts, theoretical and practical, were done in 68 and 69. You can see here, there was the idea was to change, not deposit different layers, but change some area in the material by ion radiation. So the idea was to change the refractive index of part of the material. And going to the next attempt, 1 year later, the glass fiber waveguide with core was done with core modification by diffusion or bombardment on ion implantation. And as you can see, even in this first attempt, there were similar techniques like photolithography. And here you can see in the introduction of this paper, and please remember it was 69, you can read that this paper also indicate the possible miniature forms of a laser, and it was just a few years after discovering of the first making a laser for a laser modulator and hybrids. If realized, this new art would facilitate isolating the laser circuit assembly from thermal, mechanical, and acoustic ambient changes through small overall size. Economy should ultimately result. So they were the same ideas 50 years ago, but it was not possible to fabricate them properly because of technological challenges. And now, 50 years later, these technological difficulties are more or less overcome. So we are not making just PICs in laboratories, but we are adding them in markets, in application. So here you can see the biggest markets for photonic integrated circuits. So the biggest market is optical communication and high performance computing, also quantum computing, but then is agri-food and natural resources, critical infrastructure monitoring, industrial sensing and automatization, health and well-being, consumer electronics, mobility, and space application. In this first two markets connected to optical communication and fast computing, there are few big companies working already, like Intel, Luxtera, Infinera, and they are penetrated the market. But all these markets which are not connected to the communication, they are for sensing. And also here, they are examples of working companies, and I will mention more about the examples at the end of my presentation. And if you are interested in more about applications and markets of integrated photonics, there is a white paper of integrated photonics prepared by a European Association on Smart System Integration and Photonics 21. It can be, there is a free access at Photonics 21. As I mentioned, photonic integrated circuits can be divided in different groups. Second group, not looking in the material, is dividing them in spectral range. So typically, we are dividing the photonic integrated circuits in visible range, near infrared range, and mid infrared range. Near infrared range typically is connected with telecom and datacom, but for sensing, the full range is interesting because different materials has different fingerprint in spectral range. So for sensing, the all spectrum is interesting, starting from visible, which is covered by silicon nitride and polymer platforms, through near infrared, which silicon on oxide, also silicon nitride and 3,5 materials can cover, and mid infrared, which is covered by germanium on silicon, lithium niobide platform, and also some silicon-based platforms, but without oxide below waveguide. So here you can see the typical prototyping circuit of photonic integrated circuits. So first, it is of course necessary to start with concept of photonic integrated circuits. Then next step is simulation of optical parameters of elements, and then full photonic integrated circuits. Based on that, there is need of preparing the design, the layout. After that, there is a step of fabrication these photonic integrated circuits. After that are measurements, validation, if it's working properly, and then comparison of assumptions with the results. Starting with simulation and design, what is needed? First, definition of material parameters. After that, definition of desired functional parameters. Next, definition of initial component geometry, so a lot of definitions. After that, selection of numerical method for simulation. It is important because different numerical methods are specific for different elements. And as you can see, for example, for multi-mode interferometers, the beam propagation method is the best one, and for ring resonators, FDTD method. And after choosing the proper numerical method, the iterative simulation of the component with the changes of the geometry is done. And the result of the simulation is the topography of the single elements. And here you can see the screenshot of this simulation software. So there are, on the left side, there is a model of grating coupler with optical fiber on the top. And here there is a light propagation going from the waveguide to the fiber optic. And here there is an example of geometry of multi-mode interferometer and light propagation inside this element. And here you can see the design hierarchy. So when we have single elements after some numerical simulation, we put together these elements in the circuit layout. And with this single circuit, we are putting them on the wafer, choosing the proper size of the wafer, and then we are fabricating this wafer. And here are examples of some layouts designed at Warsaw University of Technology, just to give you idea how they can look like. And now I would like to go through the fabrication of photonic integrated circuits on the example of silicon nitride. So first step is surface cleaning. After that, we have surface oxidation using low pressure plasma LPCVD chemical vapor deposition. After that, there is a deposition of surface oxidation was with thermal processes. After this was deposition of silicon nitride with LPCVD, so low pressure chemical vapor deposition. After that, resin spin coating for lithography. Next, in our case, it's electron beam lithography, but here it can be done different lithographies. It can be done, for example, with laser lithography. After that, there is a development. So we have the proper pattern in the resist layer. After that, reactive ion etching of silicon nitride, remaining resist stripping, then silicon oxide deposition. And if needed, and this is need in biosensor, there is a need of microfluidic interface. So we are locally removing the, let's say, cladding for the waveguide. So the biochemical analyte can interfere with the waveguide. And adding additional lithographies and etching, we can achieve multi-depth structures. So here are examples of fabricated elements. For example, not for example, the most important are waveguides, which are connecting the light with other elements. And as you can see, for visible light, which are interesting in biosensing, the dimensions are around 100, 200 nanometer in width, and in height it's 400, 600 nanometers. So it's a little bit challenging in technological part of view. Here you can see examples of multi-mode interferometers, right waveguide gratings, which are especially difficult because of small dimensions of the gratings. Comparison of simulation and measurements of these elements. Ring resonators, this one with opening for microfluidic interface, and also the gap between the bus and the ring here is below 100 nanometer. Comparison between simulation and measurements. And here there is a microfluidic interface, which is especially interesting in case of this seminar. And you can see this is a Mach-Zehnder interferometer with one arm covered. Here there is a one arm covered with silicon oxide, which is reference arm. And here part of the arm has removed silicon oxide, which is prepared, and this is prepared for adding some fluid. And here on this picture, you can see photonic integrated circuits integrated with microfluidic elements. The next element is fiber Bragg grating. Yeah, and Mach-Zehnder interferometer. You can see here the Mach-Zehnder interferometer with the drop of the liquid for biosensing. It was early stage of this work, so we were just adding some drops of the fluid on the Mach-Zehnder with the open arm. Okay, and grating couplers, just to showing you what is the library of element, and thermal modulators. And here are some waveguides which are suspended. So they are for mid-infrared, which is quite interesting for gas sensing, because each of gases has its own fingerprint in mid-infrared, but in that spectrum, the silicon oxide is how to say, making attenuation for the light, so we cannot have waveguide lying on the silicon oxide. So one of the method is etching the oxide or silicon from the below of the waveguide. Okay, and going more into biosensor, after this introduction for the library of the elements. So what is biosensor? The International Union of Pure and Applied Chemistry defined a biosensor as an integrated device that can detect biological or chemical substances, analytes, in a sample through specific biochemical reaction mentioned by enzymes, antibodies, nucleic acid, organelles, cell receptors, which constitute the sensitive biological elements, biological receptor. The biological receptor layers can be integrated or associated with a physical chemical transducer. The transducer converts the changes in physical or chemical properties as a result of biological interaction into a signal that can be measured and subsequently processed by an electronic circuit. So, based on physical chemical principles of transducers, the biosensor can be mainly classified into electrochemical, mechanical, piezoelectric, and what is important for us, optical photonics or photonic. So what is the idea of optical biosensor? The waveguide here, silicon nitride, is in general covered by some other material with lower refractive index. So silicon nitride more or less have refractive index around 2, and here it's covered in silicon oxide, which has more or less refractive index around 145. But if we remove the surrounding from this waveguide and add, for example, air, the refractive index will be 1. And if we add some liquid like water, the refractive index will be 1.33. And here on the simulation result, you can see there are changes in mode propagation in this waveguide. So there is a better or worse confinement of the mode. And this, with this changes, that the light interfere with the surrounding of the waveguide. And with the manipulation of the surrounding of the waveguide, we can connect this with different materials which are surrounding the waveguide. So the biosensor that have mostly penetrated the market are the electrochemical ones that can be mass produced and have low costs. Also, in recent years, a notable effort of research and development has been focused on the photonic sensors. And why they are so important? Because they have high sensitivity, wide dynamic range, good mechanical stability, ability to operate with a label-free schema, immunity to the electromagnetic interferences, and they are easy for miniaturization. The detection scheme can be classified as labeled or label-free. In labeled biosensors, the analytes are recognized by means of fluorescent dyes known as labels. Measurements down to the single molecule can be done, and a large number of labels are commercially available. Also, the extremely high sensitivity can be achieved with this technique. Its main drawback is the need of additional steps in the sample preparation before the transduction, which increase assay time and cost. The labels can also cause interference with a consequent misinterpretation of the results. Label-free biosensors like Photonics One are made of the device's sensitivity to some analyte properties, recognizing the change of one of these properties into a signal that can be measured for further manipulation. Label-free biosensors do not need any specific label to tag the analyte, so reducing the steps, the reagent consumption. Complex photonic integrated circuits with advanced sensing functions can be fabricated by the silicon photonics technology at a very low cost. Quick growing market of biochips. It is estimated around $50 billion in 2018. And here you can see some examples of this biosensor. So what is the idea of biosensor work? So first we have liquid biopsy. Then this biopsy is filtered and the biomarkers are separated by microfluidic setup. Then these liquids are dropped on some specific elements like ring resonators, Mach-Zehnder interferometers, photonic crystals. And then based on the change of the light in these elements, there is information about the concentration of this biomarkers. So the detection principles of photonic biosensor is based on evanescent wave detections. This sensing mechanism implies the waveguide functionalization through a bioreceptor layer that is immobilized on the waveguide surface. So here we have the core of the waveguide, and on the top of the waveguide and on the side of the waveguide, they are added. There is a functionalization, so they are added bioreceptors, which are catching the target molecules. Because in the liquid, the concentration of the target molecules typically is quite low, so it would be not possible to detect it by the light. But if we increase the concentration in the area of the waveguide, the refractive index surrounding the core is changed due to bigger number of the target molecule. So additional step after fabrication of photonic integrated circuits is covering the waveguide with some kind of bioreceptors which are specific for this target molecules we are looking for. And then the evanescent wave can, let's say, see the difference in refractive index. So the simplest realization of the biosensor is fabrication of Mach-Zehnder interferometer, which has one reference arm, which is covered with silicon oxide, for example, and one arm is exposed for this liquid. So like here in this picture, this one arm is reference one, this one is opening for biosensing. So we are adding the functionalization layer. This layer catch the molecules. This change the refractive index surrounding the waveguide layer, and there are changes in optical power. And we can see they are not changes in optical power, they are changes in mode transmission. And at the end of the Mach-Zehnder interferometer, we can see changes based on the functionally based on the changing of the effective optical length of this arm. So the sensitivity of the biosensor quantifies the change in the sensor opto signal produced by the unitary variation of the input seen as the sensor properly, where S is sensitivity, and N is effective index of the guided mode, and S is change in the refractive index of the waveguide cladding. The second parameter is limit of the detection, represents the minimum input value distinguishable with the certain confidence level. The first group of biosensors are interferometric biosensors, which are mainly based on Mach-Zehnder, Young, and bimodal interferometers, exhibit a very good limit of the detection, but have usually a very large footprint. Of course, this large footprint is in the world of photonic integrated circuits, where you can remember that the single photonic integrated circuits has, for example, 5 by 5 millimeter in total. So this quite big footprint make them not so attractive in the context of multi-analyte detections, because it is quite challenging to put a lot of these interferometers one by one on the single photonic integrated circuits. The optical intensity at the Mach-Zehnder interferometer output is proportional to the cosine of the phase shift between the beam recombination at the output. By measuring the optical intensity at the interferometer output and consequently the effective index change, the effective index change can be estimated with the high accuracy. Since the effective index can be correlated with the analyte concentration, the Mach-Zehnder sensor provide a very precise measurements of the target molecule concentration in the sample. An interesting advantage of this element is possibility of using a long light matter interaction length, where we increasing the biosensor sensitivity. So it is quite easy to make them even larger for better sensitivity. And here are examples of Mach-Zehnder interferometers fabricated in CEZAMAT. And additionally, we can modify the Mach-Zehnder general interferometers, adding a slot waveguide. So this slot waveguide, this is the area where there is a small gap added inside the waveguide. So more light is going outside the waveguide. So the bigger part of the light is interfering with this the liquid covering the Mach-Zehnder interferometer. Not only liquid, but it can also apply to the gases, because all this microfluidic application, in more or less in general, they are the same for gas application. Of course, if the gas concentration is big enough. So here you can see the cross section of the slot waveguide and the simulation of the simulation of the light going outside the waveguide. So here the light is propagating mostly in the slot between these two waveguides, so it can more interfere with the liquid which is covering the waveguide. Okay, the second group of the biosensor elements, they are resonant biosensor. They have high sensitivity and small footprint, in contrary to these interferometer devices. And it has the small footprint has been obtained with a label-free photonic resonant biosensors because of the stronger light-matter interaction. By assuming as a figure of merit, the best performance has been reported by microring resonator and photonic crystal-based biosensors. You can see in this picture that this is example of biosensor. It was just for testing technology. That's why it has not connection for their waveguides, but you can see there are 10 microns on the scale. So this element in total has something like 100 by 100 microns. So it's much more smaller than Mach-Zehnder interferometer. And in ring resonator, the light is coupled by an input bus waveguide in circular waveguide ring, where it's propagated as a whispering gallery mode, generating a constructive interference and then a resonant condition when the round trip phase shift equals an integer time 2p. So the formula for resonant wavelength is effective index multiplied by physical length of the ring and divided by integer number. The whispering gallery mode circulates around the resonator, and its evanescent field repeatedly interact with the analyte approaching the resonant surface. The variation of the physical properties of the functionalization layer induce a variation of the effective index of the mode, and this in turn cause a shift of the resonant wavelength that can be correlated to the concentration of the target analytes immobilized on the surface. The interaction with the target's analytes is strongly enhanced by the number of revolutions of the mode with the ring, which is as high as the resonance quality factor Q is high, achieving a very long interaction length. This determines very high resolution of the biosensor based on ring resonator. The resonator efficiency is described by the Q factor, which depends on the total losses and is derived experimentally by dividing the resonant wavelength by its full width at half maximum. And here there is an example. There is an idea and examples of biosensors based on ring resonator. So here we have the ring resonators with surface after biofunctionalization. Adding the analyte, the target molecules are binding to the surface. It's changed the refractive index surrounding the ring, and here we can see the shift of the peak for the transmission in ring resonator depending on the refractive index changes. So even small changes like this one, 1.29, 1.30 are possible to detect. And here you can see the picture of the fabricated ring resonators with the openings for adding the chemicals on the top of them. And the modification of the ring resonator is adding the sub-wavelength grating devices, which cause the bigger part of the light going outside the waveguide. So the evanescence light is increasing. But also, as similar to the slot waveguide, they are technological challenges because the critical dimensions of these changes are smaller than or similar to 100 nanometers. So it's starting to be difficult to fabricate them, even with the CMOS technology. And the next group of biophotonic elements are photonic crystals. The photonic crystals are basically structures with a periodic arrangement of the material of different dielectric constants with a periodic of the order of the light wavelength and characterized by the transparency of photonic bandgap. A light wave at the frequency with the gap cannot propagate in the periodic structure, and periodicity can occur in 1 dimension, 2 or 3 dimension, and defines the wavelengths that the structure can support. By introducing a defects in the structure properly designed, a photonic cavity can be easily realized with strong confinement of the light in the region of the defects and its surroundings. So this is another, let's say, element where we are first defining the photonic path, then squeezing light to going outside the waveguide and interact with the surrounding and detect the changes of this light. And then there is a integration with microfluidic system. So we have the photonic integrated circuits. And next thing is adding the microfluidic system, which are applying these fluids on the top of the photonic integrated circuits. So first thing is proper functionalization of the chip. Then the microscale fluidic mechanics, because in the small dimensions, the fluidics, they are starting to act not, let's say, similar in our work. There is need of choosing the proper material. So the material of microfluidic system is not interacting with photonic integrated circuits. Then there is need of fabrication of 3D shape, because as you remember, let's say the ring resonator is 100 by 100 microns. So the microfluidic system, which is adding the fluid on the top of it, need to be also quite small. And if you want to have many of the devices on the one circuits, we need also have the many microfluidic mechanism adding the liquids on the top of the ring resonator. So there is a need of precise fabrication of these 3D shapes for these liquids. Then there is integration with the PICs. So we need to somehow bound this microfluidic mechanic system on the top of the PICs, and there is many more complications, like adding light and detection of the signal of this starting to be quite complicated systems. Here you can see the idea of photonics package. The role of this photonic package is to make a mechanical protection of the integrated circuits, making the optical and electrical interface, make an encapsulation for this whole optical and electronical system, and stabilization of the operating of the temperature. So here you can see the photonic circuits, optical fibers added to this, wires and bond pads for the PCB for electronical connection to apply power to the system, the heatsink, and the thermoelectrical cooler, and also, it is important, there is no microfluidic in this example. So somewhere on the top of this packaging, which is already quite complicated, there is need for microfluidic system. So it's starting to be quite complicated. And here you can see some photos of photonic package. And based on, of course, on the applications, it can be bigger or smaller, or it can be encapsulated in one box, like here or here, or there is an entire board for different elements to add light, to make a readout system for the detectors. And the photonic integrated chips, honestly say, they are one of the smallest part in these examples. Like here, this is a photonic part. Here, there is a photonic part. And as I think here, there is a photonic part. So you can see the comparison between the full board and the small photonic part here. And now they are examples of photonic integrated biosensors. To refresh for what they are for diagnostic, medical, and biosensor research. They are for environmental monitoring and protections, crops and food production monitoring, operating parameters of industrial line monitoring and quality control, then occupation health and safety. And here you can see the idea of biosensor. So here, starting from the photonic part, photonic integrated circuits part, here we have some integrated lasers here, single mode waveguide. Here we have Mach-Zehnder interferometers with biofunctionalization, which catch the proper molecules. Depending on biofunctionalization, they are catching different molecules. You can see here they are yellow, blue, and green hands, let's say, which are catching different elements. Then the signal go to the grating coupler arrays and to the camera. And what we have on the external, we have the external pumping for the laser and the cartridge, because this part is changeable. So please imagine the device when you are switching the photonic integrated circuits, and you have one external pump and camera which detect the signal. Here there is another example, but based on the same type of optical elements. So we have Mach-Zehnder interferometer with sensing arm, which are catching biomolecular, and the reference arm. And here go light from the outside source. And there is a CMOS camera which is checking the changes of the light going from this Mach-Zehnder interferometer array. Again, example for the assessment of the gold mic adulteration with a label-free monolithical integrated optical biosensor. So you can see there is added there is added white LED, which launch the light into the Mach-Zehnder interferometer again. So you can see more or less all these sensing elements are based on Mach-Zehnder interferometer or ring resonators. And here there is a example and the photo of a low-cost integrated biosensor platform based on silicon nitride nanophotonics for biomarker detection in urine. And you can see there is a photonic chip here and much bigger microfluidic system, which is applying the fluid to the photonic chip. So the maintaining on the fluid go on the fluid road on the system is quite challenging. And there is also the fighter and the bubble trap for this system. And what is interesting, there is need of additional light source and detector. So even the system is quite big, there is a need of additional light source and detectors which are not presented. And here one more example, which much more system for based on Mach-Zehnder interferometer for real-time label-free monitoring of biomolecular reactions. And again, we can see there is an array of Mach-Zehnder interferometers with different biofunctionalizations. External light is launched. It's go through the Mach-Zehnder, and then it's go to the photodetector. And based on this photodetector results, we are checking if there was a change of the concentration of the specific molecules. And here are examples of applications. There is a company Indigo, which is a Belgian startup. It produced the multi-metabolic sensors. This is spectrometer on a chip, measure glucose, ketone, and lactate levels in people living with diabetes. It's continuous measurements with being implanted under the skin. Helps people with diabetes to live more normal life without the need of external monitoring system. The next system is European project CARDIS. This is a prototype medical device to screen areal stiffness and diagnose cardiovascular disease. It's based of low cost. It's based of very low power laser. It's directly to the skin. It's based on low power laser, which is directly checking the skin overlying the artery, the skin vibration amplitude, the frequency resulting from the heartbeat, and extract from the Doppler shift of the reflected beam. The device includes 2 rows of 6 beams, thereby scanning multiple points of the skin above the artery in parallel. The next example is the photonic biosensor device for cancer treatment monitor, and it's device based on Mach-Zehnder interferometer. There is a VCSEL on the top of the grating coupler, which launch the light, and there is this. The sensing is performed by measuring the phase shift of the optic signal caused by the binding of the analyte of the functionalizate of the Mach-Zehnder interface. And again, the diagnostic tests for early detection of and monitoring of the cancer. It can detect the multiple biosensor at the same time. The receptor molecules that are coated onto the surface of the photonic biochips can be selectively catch and bind specific biomarkers into sample based on the biorecognitions. And next one, there is a Broyles integrated circle. It's swept wavelength infrared laser absorption spectroscopy. Each molecule has a unique absorption spectrum due to its various rotation and vibration movements, and absorption spectrum is used as a fingerprint for specific and concentration identification. Here there is an example of backside on box, the seamless integration of laser and optical amplifier, combination of silicon and indium phosphide materials, which combination is needed if you want to have active and passive elements in one chip. And this is a solution for the pain of the standard silicon photonic lacking lasers. Okay, and there is a multiplex disposable photonic sensor platforms. And last example, there is a fiber Bragg grating fiber sensor system based on ASPIC. This system is sending light into optical fiber, so there is no. It's not directly interfering with the analyte or the other thing. It's sending the light to the fiber, which typically has a Bragg grating, and the sensor reflect the light back to the integrated circuits. With that thing, it is possible to measure the strength, temperature, pressure, shape, and vibration of the brack grating on the fiber. Okay, and going a little bit outside of the biosensing, they are LiDAR system, which are considering as a critical sensor in the automotive system. And this is like the key enabling, the photonic integrated circuits. This is a key enabling technology for that solution. And the last slide in my presentation, it's reminding of the INFRACHIP. Warsaw University of Technology is part of the INFRACHIP, so some of elements which I was presenting, it's possible to fabricate in our facilities. So I encourage you to contact for fabrication of them. Thank you for your attention.
All right, thank you very much for this presentation. This seminar is now open for the questions. So there is the question and answer facility that you can find at the bottom of the screen. And if you type your questions there, we will try to answer them. So let's give it a minute or two for people to try to figure out a question. I think in the meantime, I can ask you kind of a more general question. So when you talk about the biosensors, so in your platforms, are you taking care of, let's say, the biosensor part, sort of including the microfluidics, or are you also doing the biofunctionalization? So do you also attach the DNA or the antibodies, or is that something that external people do? So
okay, in our group, we are focusing on fabrication of the photonic integrated circuits. But in CEZAMAT, they are dedicated groups for biomedical research, and they can make a biofunctionalization. So as at CEZAMAT, we have capability of making photonic integrated circuits and then making of the functionalization of them. So it's like full package of work in case of the biosensors. But what is important, I think, to remember that we are working on the passive platform. So it is not possible to integrate in silicon nitride, germanium on silicon, directly integrate lasers and biosensor, laser and detector in the same chip. So this complicates a little bit of the biosensor idea.
All right. Thank you. All right. So we have the first question from the audience. What is the maximum voltage rating for PIC?
Maximum voltage. I'm not sure if I understand properly this question, because if we are thinking about the passive platform, there is no photodetector and no laser, so only we are applying voltage for the modulation of the thermal modulation in silicon nitride, and they are the voltage is applied by the material, the metallic puffs. So as thick and big as thick and tough the puff can be, we can apply the voltage. So I'm not sure if I understand properly the question and answer it.
All right. Well, perhaps so. If okay,
Dimitri, Wasim can open the mic if needed to further explain the question.
All right. Well, okay. Let's say so. It looks like maybe that would be a good, maybe that would be simpler.
Of course.
Wasim, if you want to talk, yeah, because it looks like you have some questions here. All right.
Mm-hmm.
Okay. Okay. Thank you for giving the opportunity to ask a question. I want to ask the voltage rating about the integration of sensors. I can say, sorry, fabrication of sensors. The required voltage for this.
Okay, so we made some experiment in our platform. We made some experiment with thermal modulators, and we were adding several voltage for the like 12 or 15 volts on the peaks to hit this, and there was no problem with that type of voltage. But we didn't try to go higher with the voltage on the peaks.
So I want to ask, can we do this at lower voltage? This is the you can say fixed voltage, or we can do it on the lower voltage.
Sorry, can you repeat the last sentence?
Can we perform this on lower voltage, or this is the fixed voltage?
Yes, we can perform this on the lower voltage. There's no problem. We were just checking how high we can go without the breaking of thermal modulator. So it is possible to go with the lower voltage. But of course, it depends on the application, what you are thinking, and depending of the materials which are needed, because we can make these metal elements from the different materials, from the aluminum, gold, titanium, depend on what is needed and what is possible in the laboratory.
All right, thank you. I guess a related question was actually about interfacing a temperature sensor with a PIC.
Okay, for silicon nitride, which I am most familiar, it is quite difficult to make the temperature sensor, because especially silicon nitride can handle really, how to say this, it's quite strong immune for temperature changes. So this element is not changing, the elements made of silicon nitride doesn't change the temperature parameters, its parameters with the temperature. So silicon nitride, they are not so good as a temperature sensor. As I know, the 3.5 materials, they are more sensitive for temperature changes. So the 3.5 platforms are more, I would say, suitable for that type of sensing element.
I think maybe I can ask a follow-up from my own experience. I think one of the reasons, right, why a good temperature sensor could be interesting is that temperature changes, of course, is one of the ways that you can change the effective index of refraction of, for example, the fluid sample. And so if, for example, when the sensor is operating, it warms up a bit the sample, then the index of refraction will change, even though it would not necessarily apply the actual interaction or something like that. I don't know if you have encountered those kinds of situations in your experience.
With the biosensors, not, but we were fabricating the Mach-Zehnder interferometers based thermal modulators. But it was needed to make a quite big temperature change to see the change in the light signal. So it was a lot of heat needed to change this signal. But it is a silicon nitride, what we have material which we have experienced. So it's quite resistive to heat, I would say. But of course, the proper biosensor made with the packaging. There is a standard for in the packaging. This is a standard thing to have a thermal stabilization system based of Peltier module or heatsink. So this is a standard thing even in butterfly package to have a thermal stabilization system. So of course it's important to do if we think about the application, not just measurements in laboratory.
All right, thank you. Again, I think that one of the reasons why it's an interesting question is because, of course, in some other sensor platforms, let's say the temperature sensitivity is something that you can never really get rid of, but at the same time, it also means that you basically get a temperature measurement for free. Again, whether you want it or not,
yes,
it's always going to be there.
Of course.
So it's important to note that depending on the specific sensing platform, the effects
of course
are different. All right, let's see. So let's give another minute if people come up with some additional questions, because I'm also aware that we're a bit over time right now. All right. Well, if there are no other questions, then I thank everyone for joining the seminar today. Again, these seminars are supported by the INFRACHIP project. So make sure if some of the platforms or some of the ideas that you saw today looked interesting or potentially interesting for your research, then you can get in touch with us. You can also, of course, to register for this seminar, you already have been to the infrachip.eu website. So you can go to the website and submit a question and so on. And of course, we will try to make sure that your questions are answered, whether it's related to the specific technology or whether it's related to things that are offered by the other partners. And of course, this is the second seminar in a series, so we're going to have 2 more. So we basically have them on the same day of the week and time in November. So thank you for coming to watch this one, and I hope that you come back and join us for the other 2. And it doesn't look like we're having any more questions. So I thank everybody for attending, and we'll see you next week.
Thank you very much. Goodbye.